Hello, this is the third video of the Algorithm 3 series on further algorithms and efficiency for OCR Discrete Further Mathematics. And we will look further at the order and efficiency of a quicksort algorithm. In the previous video, we saw that it took 14 comparisons and 3 passes to sort a list of 8 numbers in the first example, but 36 comparisons and 7 passes to sort a list of 9 numbers in the second example, both using the first elements as pivots. Now we look further at the choice of pivot influencing the efficiency of the algorithm for specific lists. In this example, if we use the first element or pivot, we make 6 comparisons, 5 comparisons, 4 comparisons, 3 comparisons and 1 comparison, totaling 19 comparisons and 5 passes. Note that the first 2 pivots happen to be at the extreme ends of a range of numbers in the list. So for numbers range between 1 and 12, those are the highest and the lowest number. Using the middle element as pivot, we see that only 2 passes and 6 comparisons and 4 comparisons, totaling 10 comparisons in all, are needed. Note that here the numbers 4 and then the next pivots 2 and 8 are nearer to the middle of the range of the numbers in the list. In practice, quicksort algorithms choose the pivot element randomly. In the previous video we saw that the quicksort for this list, sorting it into ascending order, was 14 comparisons and 3 passes. Bubble sort for the same list totaled 25 comparisons and 5 passes, whilst the shuttle sort took 18 comparisons and 7 passes. So just one way to evaluate the relative efficiency is to look at the number of comparisons required for each sorting algorithm on the same list of numbers. And we found that Bubble 25, Shuttle 18 and Quick 14. So it looks as if the quicksort is the most efficient. But whilst these results give us an idea of relative efficiency, further analysis would be needed to draw firmer conclusions, as various other factors also affect efficiency. To illustrate the overall complexity of bubble and quicksort algorithms, let's look at the runtime of each algorithm for various array sizes in 3 very different situations. So, first, when the array is already sorted, which leads to best case scenarios for some algorithms, or when the array is already sorted but in reverse order, which can lead to worst case scenario for simple algorithms, and then thirdly, when the array is randomly ordered. So in this comparison of a runtime in those 3 scenarios, you'll note that we're only comparing here the bubble and the quicksort, that the top row in each table gives the number of items, or the size of the problem. The time is given in microseconds, and where there is missing information, the researcher did not have the patience to wait for the results. Note that the bubble sort is faster when the array is sorted. And the worst case is when the reverse is reverse sorted. On average, the quicksort is faster unless you have the worst case scenario, but this is quite rare. Also note that the quicksort is sensitive if order happens to be correct at the start, as seen in the previous video when we were arranging the digits 9 to 1 in descending order, but they were already in order. So, the divide and conquer nature is taken full advantage of if we have a randomly sorted array. However, if a pivot happens to be smallest or largest number in the list or sublist, then the list will need to be broken down n times and n to the minus 1 comparisons made each time. So the worst case scenario for both quicksort and bubble sort is order of n squared. And indeed the bubble sort average is order n squared and the best case scenario is order n. Whilst for the quicksort the average is order of n log n, which is the same as the best case scenario. So quicksort is generally more efficient than bubble and shuttle sort. Quicksort works best when the pivot happens to be in the middle of a range of values in the list. If the pivot happens to be the smallest or largest number in the list or sublist each time, then you get that worst case scenario on order n squared. In the next video, we will return to packing algorithms, but bin packing in 2 dimensions.